Hello, Tensor friends. We got some confusion here over, I think it's over wording. I really do. Because I think you know what you're doing. I think you're just confused over words. Okay? I'm going to try to do this freehand. And my writing is terrible, so I apologize ahead of time. Okay, what we're talking about here is covariant transforms and contravariant, the transforms, right? So let's just start from the beginning. We have a position vector that is a function of some arbitrary coordinate. Now, we want to transform that vector into a prime, the system which makes that arbitrary, the coordinate, a function of, oops, see what I mean? J prime, right? So we have a, what do you call this? A compound argument here. So if we take the partial derivative of this vector, boink, with respect to that coordinate, over here, using the multivariable chain rule, we can write this like this. Okay? So this is equivalent to this because of the chain rule. Well, what is this? We know what that is, right? This is the basis vector EJ. The derivative of a position vector with respect to a coordinate is a basis vector. Well, what's this one? This is also a basis vector, but it's EJ prime. And what's this thing? This is a new thing, right? And we've seen it before. It's called the Jacobian. So it's a capital J, J prime J. Okay? So look at this. There's one free index, and it's in the covariant position. And you see here it's in the covariant position. So this becomes a summation index, right? So any vector that transforms like this is called a covariant transformation, right? So the key word here is the free index on this one index, the tensor, is in the covariant position. So this is a covariant transform, right? If I do exactly the opposite of that, let's say I have any vector, let's call it t, and it has a contravariant index, well, this is going to transform exactly the opposite. T, I prime, J, I prime. Right? So there's one free index, I and I. Now the summation index goes this way, and look at it here. It went this way. So this is a contravariant transformation. And that's all it means, right? That's all it means. There's nothing sexy going on here. It's just the wording of how they. It's from the old school days of they called everything contravariant and covariant instead of the new terminology, which is just vectors and covectors. Okay, so let's go to another page and do this as an example. Okay, we'll go to this new page. All right, so we said that I forgot what I said. I got EJ. Okay, we got EJ is equal to EJ prime times J, the capital J. I got too many J's in this. I should have used I. I'm going to use I. What a nerd. EI, that's the basis vector, is equal to EI prime times the Jacobian. Now see, here's the free index, I prime. Okay? So let's let the unprimed be r and theta. So this is unprimed. And let x and y, so we're going to go from Cartesian to polar, be the primed. Okay? So let's just do one example here. So this is ER, the basis of the vector, and this becomes EJ x, right, because it's primed in the first case. I'm going to do it like this first. EI prime, JI prime. Now look here, we've got a free index. So now I have to expand this summation index, right? So it's going to go EX in the first case, XR. Always have to have that same, plus E, what's the second one? Y. J, what's the second one? Y. R. Okay? Now, remember our transpose equations? We had that X is equal to R cosine theta, and Y was equal to R sine theta. Okay? So we can do this because this is equal to EX, what's this? The partial of X with respect to R plus EY times the partial of Y, see here, YR with respect to R. All right, so if we write this, we got the ER basis vector is equal to this term, the partial of X with respect to R, which is what? Just cosine theta. I don't need those. EX here plus the partial of Y with respect to R, here's Y, just sine theta EY. So this is the covariant transformation from Cartesian to polar, right? And we can do theta the same way. Let's do that one in our heads. Okay, so it's going to be EX, and this will be the theta, X with respect to theta, Y with respect to theta. So what is the partial of X with respect to theta? It's minus R, see here, sine theta EX. What's the partial of Y with respect to the theta? It's just R cosine theta EY. So there's both base the vectors, right? Now, let's do a contravariant in polar coordinates also. I did that already. Here's a new one. Okay, so let's say we have some component and it is contravariant because it's part of a vector, right? So we have a vector which is V contravariant I EI basis vector, right? So let's do this one. So how would I do the transformation? Well, I would have, first of all, my Jacobian. I have to put the index in the same place, so I put it in the contravariant place. Then I do the prime, the system, and then I put VI prime, right? So here's my summation index, and here's my free index. So let's say I wanted to do VR. How would I do that? All right, so my Jacobian would be JR, has to be the same here. We're going to Cartesian, so it's going to be X VX plus J, R has to be the same, R Y VY. Okay, and what's that mean? That means we need the partial of R with respect to X plus the partial of R with respect to Y. Oops, I left out my terms here, Vx and Vy. Okay? So in that same, the transform equations, what is R? R is equal to x squared plus y squared to the 1/2. All right, so what is VR is going to be the partial of R with respect to H. What's that going to be? That's going to be 1/2 times what you got minus 2/2 would make this minus 1/2. And then derivative of what's inside is 2x, so that cancels that. And we get what? X over square root of x squared plus y squared. And that's just R. So we got x over R. And what's x? That's from the slide was R cosine theta over R. So we just get cosine theta. Now what's V? What's I going to do? Oh, partial. What is the partial of Oh, this is not equal to that. This is just the partial. You're getting ahead of yourself here, dude. Get rid of that. Get that back. Now we need the partial of r with respect to y. And by symmetry, you're going to see that this is just going to be y over r. And y was r sine theta. The r's cancel, so it's just sine theta. So we can go up here and write VR is equal to cosine theta Vx plus sine theta Vy. Okay? So here we did a contravariant transpose. And over here we did a covariant transpose, right? All right. I hope it helps. If it doesn't, let me know. I think it was just wording. I think you know what you're doing. All right, I'll see you later.